We're interested in prismatic bars. By prismatic we mean straight and uniform cross-section, subject to moments along the axis of the bar. We call these kind of moments torque. So here we have a bar that is subject to equal and opposite moments along the axis, and it's preferable to represent the moments with two arrows like this to avoid ambiguity. In undergraduate mechanics courses, only a very special cross-section bar was considered, namely a circular cross-section or a cylinder. What's so special about a circular geometry? So if we draw a grid like this on the surface of the cylinder and apply a torque, we see that what was circles has to remain circles after application of the torque because of the axial symmetry of the bar. The circles cannot get distorted. On the other hand, if we subject a bar that is not circular cross-section to a torque, there could be warping. Because there's in general no axial symmetry, there's nothing stopping the section from warping like shown there. So this kind of warping can be free to occur or it could be constrained. For example, in this I-beam, the warping is constrained. So we can think of torsion as in different scenarios: circular cross-section, non-circular cross-section, and under non-circular cross-section when warping is free or when warping is constrained. When warping is free, we call this Venant torsion, and that's the situation we'll be exploring in the rest of this assignment. So the question we're interested in is if we apply a torque T to a non-circular cross-section bar, what's the relative rotation between the ends, and what's the maximum shear attraction on any cross-section. So if we take a bar of arbitrary cross-section, non-circular, such as this, and apply a torque to it, the way we'll approach addressing the above questions is to think of this bar as a general three-dimensional continuum, and therefore it has to satisfy all the governing equations of a three-dimensional continuum, and those equations are represented by the Tonti diagram that we considered in assignment 2. But solving this system of equations implied by the Tonti diagram in general is difficult. So what we'll do is we'll guess the solution, and then we will go through and see that it satisfies all the equations. And if we can find such a solution that can satisfy all the equations, then some uniqueness theorems guarantee that that's the only solution. This is what we'll take up starting in the next video.